Welcome back, and in this fundamentals lesson, I want to step you through how to convert decimal numbers into binary and back again, specifically relating to IP version 4 addresses. Now, if this is something which is new to you, I really suggest taking this slowly and focusing on each step of the process. If you don't understand something, just pause, think about it, and if needed, restart the video. I promise, once you can do this process, it will really help you with networking. The process is easy once you've done it a few times, so I want to explain it as simply as I can at first and then suggest that you get some practice. So let's jump in and get started. Before we start with the actual process, I want to set the scene as to why you need to understand it. When dealing with IP addresses as a human, you might see something which looks like this. 133.33.33.7. This is an IP address represented in what's known as dotted decimal notation. 4 decimal numbers ranging from 0 to 255 separated by periods. So that's what a human sees. A computer sees this. The same IP address, but in binary. Now this is actually a 32-bit binary number, specifically 4 sets of 8 bits. Now 8 bits is known as a byte, each byte is also known as an octet, but crucially it's the same number as the decimal version. To understand much of how the Internet Protocol works, so things like IP ranges, prefixes, subnet masks and routing, you have to be able to convert between the two, so decimal and binary. All of these things only make sense when viewing IP addresses in binary. So when it comes to networking, being able to convert between decimal and binary or vice versa really is a superpower, and that's what I want to teach you in this lesson. So let's move on. I want to start with the process of converting a decimal IP address into binary. This is actually the more complex direction. Decimal to binary is confusing at first, whereas binary to decimal is much easier. When you're just learning this process, I find that it's easier to tackle it in bite-sized pieces. Let's say that you want to convert this IP, so 133.33.33.7 into binary. Well, each decimal in between the dots, so 133, 33, 33 and 7, is a number between 0 to 255. So I find it easier, at least initially, to tackle each one of these numbers individually, working left to right. So that's what we're going to do in this lesson. I'm going to step through the maths involved to convert 133 and 33 into binary, and then I'm going to ask you to follow the same process for the last two numbers. Now, before I step through this process, let me introduce this table. This helps us with binary maths because it tells us what the decimal value is for each position in binary. Now, this table has 8 positions shown as 1 to 8 on the table, and so it works for 8-bit binary numbers. Remember, each part of an IP address, each number between the periods, is actually an 8-bit binary number. Now, each position in this table has a value, so 128, then 64, then 32, 16, 8, 4, 2, and finally 1. It means a binary 1 in that position has the associated value in decimal. So a 1 at position 1 is 128 in decimal, a 1 at position 4 is 16 in decimal, and a 1 at position 8 is 1 in decimal. We're going to use this table to help us convert decimal numbers into binary. We're going to move in the table from left to right, starting at position 1, moving through to position 8. At each position we're going to follow a process. It's going to be the same process with a number of rules, and if you learn how to follow these rules, it makes the conversion really easy. So once again, for a given decimal part of the IP address, so in this case the first one we're going to look at is 133, we're going to work through this table left to right. And as I mentioned earlier, I'm going to demonstrate the process for 133 and 33, and then you're going to follow the process for 33 and 7. So we start on the table in position 1, we compare our decimal number, so 133, to the value in the current position of the table, which is 128. Now rule number 1 is that if our number is smaller than the corresponding binary position value, then you write 0 in that position of the table that you're in this case position 1, and then you move on to the next position, starting processing using rule number 1 again. However, if our number is greater or equal to the binary position value, then rule 2 applies. Now this is the case for us because 133 is more than 128. So what we do is we minus the binary position value, so 128, from our number. So that means 133 minus 128. This leaves us with 5. So 5 is the remaining decimal value that we have. And then we write a 1 in this column and move on to position 2. A binary 1 in this position is equal to 128, so all that we've done is transfer 128 of the decimal value into the corresponding binary value. So we've added a binary 1 here and we've removed 128 from our decimal number, leaving 5. And now we can continue the process to convert this remaining 5 into binary. So now we reset the process, we move to position 2 in the table and start evaluating again using rule number 1. So we're comparing our remaining value, so we have 5 in decimal, against the binary position value in position 2, which is 64. So now we compare our number, 5, to the value in the table, which is 64. So in our case, our decimal value of 5 is smaller than the binary value of position 2, and so we're using rule number 1. We add a 0 into this column in the table, and then we go right back to the start of the process. We move on to position 3, and we start evaluating against rule number 1. We repeat the same process for positions 3, 4 and 5. Our decimal value of 5 is less than all of those values, so 32, 16 and 8, so we add a 0 in each of those columns and we move on. So we've evaluated all of those and they match rule number 1, and so we add a 0 and we move on. We're just following the same basic rules. So now we're at position 6 in the table. We compare our remaining decimal number, so 5, against the value in position 6, which is 4. Now it's not smaller, so we move past rule 1. It is larger or equal, and so we use rule number 2. We add a value of 1 in this binary position and minus this binary position value from our number. So 5 minus 4 equals 1. So we have 1 remaining in decimal. A binary value of 1 in position 6 is equal to 4 in decimal. So we've just added this to the binary number and removed it from the decimal number. What this process is doing bit by bit is removing value from the decimal value and adding it to the binary one. First it was 128 of the decimal number, and just now it was 4 of the decimal number. And next we move on to the next position in the table. So now we're looking at position 7. We're comparing our remaining decimal value of 1 with the binary position value. First we're evaluating against rule 1, and because our remaining value of 1 is less than the binary position value, we use a 0 in this column and we move on to the next position. So now we're on position 8. Again we do a comparison. Our decimal value is 1, the binary position value is 1, and so we evaluate this against rule 1, it's not less. We evaluate it against rule 2, it is equal or larger, and so we add a 1 in this column of the table, and then we remove the binary position value from our decimal value, so 1 minus 1 is 0, and because we have 0, the process is finished. And this means that 133 in decimal is expressed as 100000101 in binary. Now this is one example, so this is converting one part of an IP address. Let's run this process through again with the next part of this IP address. So this time we're converting the second decimal part of the IP, so 33, into binary. We start again with our same process and our same table, and we move through the table left to right. We start with position 1, we compare our decimal number, so 33, to position 1's value, which is 128. Is our number less than 128? Yes, it is, and so we use rule number 1. We add a 0 into this position of the table and then move on to position 2. We compare our decimal number to the value in position 2. Is our number less than 64? Yes, it is, and so we use rule number 1. We add a 0 into the table and move on to position 3. We compare our decimal number, so 33, to position 3's value, which is 32. Is our decimal number less than 32? So no, it's not, so we skip rule number 1 and move to rule number 2. We minus 32 from our decimal number 33, leaving us with 1. So we've transferred 32 of the decimal value into the binary value, and then we move on to position 4 in the table. Now I hope at this point you start to feel more comfortable and we can speed up. At this point we're at position 4 and we can simply repeat the process. We compare values. If our remaining decimal value is less than the value in the table for that position, we add 0, and this is the case for positions 4, 5, 6 and 7. So we add zeros into all of those positions. Then finally we have position number 8. We compare our remaining decimal number, which is 1, with the value in position 8, which is also 1. Is our value less? No, it's not, so rule number 1 isn't used. Is our value larger or equal? Yes, it is, and so we use rule number 2. So we write down 1 in position number 8, we minus the binary position value, which is 1, from this number, leaving us 0, and that means we finished the process. So the binary value for 33 is 001 00001. Now I want you to try and do this process on your own on some paper for the third value of 33 without looking at this lesson. This process is the same, but it will let you practice yourself. And once you've reached the same value as me, you can follow the same process for the fourth decimal value of 7. Once you've done them all, you'll have the full 32-digit binary number, which represents 133.33.33.7. So go ahead and pause the video and do the final 2 calculations yourself, and you can resume it once you've finished. Okay, so I hope that was pretty easy for you, and what you should have for the last decimal value of 7 is a binary value of 000000111. If you did, awesome. That means you've completed it successfully. If not, don't worry, just watch the first parts of this video again and repeat the process. Now at this point I want to show you how this works in reverse, converting binary to decimal. This time let's say that you want to convert this binary IP address into decimal. So both of these are one and the same. To start with, we break the IP address into 4 sections, and this is the same for the binary and the dotted decimal versions. So each decimal part between the dots represents the corresponding 8-bit binary value. So I've coloured these in red, blue, green and yellow, so left, middle right and right. So this is one and the same. They're the same IP address expressed in binary on the left and decimal on the right. Now just as before, the easiest way to tackle this is to work left to right, working on 1 octet one by one. The process for converting this in this direction is much easier. We have the conversion table just as before. Each binary bit left to right has a value. 1 to 8 on the left and 1 on the right, and we read them one by one. So in each of the 8-bit binary components, so each of the different coloured squares, we go through from left to right and we look whether there's ones or zeros in each position. If there's a 1, we take the corresponding number from the table at the bottom of the screen. So the first example, the 1 on the left, represents 128. So we write that down. We write 128 and then a plus. If there's a 0, and this is the case for the following 4 bits, so 0, 0, 0, 0, then we add a 0 in our equation. So we have 1 to 8 plus 0 plus 0 plus 0 plus 0. Then we have another 1, so we look at the table at the bottom for the corresponding binary position value, in this case the number 4, so we add that. Then we have a 0, so we put 0, and then we have another 1, so we again look for the corresponding value in the table, which is a 1, and we add all of those together to get the result. In this case, 133, so this represents the first part of the IP address, and we follow the same process for all of the remaining parts. So 001000001 represents 33. We just take each of the ones in each of the components of the IP address and look up the corresponding binary position value in the table. So in the second component of the IP address, there's a 1 in position 3, which is 32, and a 1 in position 8, which is 1, and this represents 33. The same is true in the third component, and in the fourth component, there's a 1 in position 6, 7, and 8, which represents 4, 2, and 1. So we add 4, 2, and 1 together to get the resultant value. So if you follow that process bit by bit for each 8-bit component of the binary IP address, then you will end up with the dotted decimal version of the IP address, which is exactly what we've done here. So why don't you go ahead and pick a random IP address and follow the same process through and see if you get the correct result. And then once you have the correct result, take that dotted decimal IP address and follow the previous process to convert it from decimal to binary, and you should end up with the same result that you started with. If you do, that means you understand the end-to-end process of binary to decimal and decimal to binary, and I promise you later in the course, and whatever you're using AWS for in the real world which involves networking, this does represent a superpower, so it's really important that you understand. At this point though, that's everything I wanted to cover, so go ahead and complete the video, and when you're ready, I look forward to you joining me in the next.